Now we have the simple algorithm of a linear Kalman filter. But there are many questions that needs to be answered. For example, what are Q and R and how can we quantify them? Are they fixed? What if the system is nonlinear and we cannot write the state space equations in a matrix form? What should we do in that case? For example, we don't have any C here to calculate the variance of the updated state. And these are the things we need to answer. And if we want to use a Kalman filter for a complicated system, which we talk about in the coming videos. Now I'm going to see how can we use this Kalman filter algorithm, simple Kalman filter algorithm, for a state estimation task. Now we jump into the next slide. We have the traditional damped mass spring system. We install one accelerometer sensor on the mass and measure the acceleration of the vibration of this 1 degree of freedom system. We know the equation of the motion of this system as well. Then we have some sensor data, which is coming from the sensor attached to the mass. We have the equation. If we assume we know the stiffness value, damping value, and mass, and measure the x double dot, which is coming from the sensor data, can we estimate x and x dot? Why don't we just go and integrate it? Because the sensor data we have is super noisy. And if you integrate a noisy signal, you're never going to get the true display velocity and displacement signal. For this reason, we want to see if we can use Kalman filter for this task or not. First of all, we need to transfer the equations and write the equations into the state space form. And to do that, what I do, I define two variables, x1, which is x, which is displacement, and x2, I define it as x dot. Again, I repeat, to convert a second order ordinary differential equation to a state space form, you can find the technique in any control book. And here, I'm just going to explain it for this simple case. Then I assumed x1 is equal to x and x2 is equal to x dot. Then this means x dot 1 is equal to x2 and x dot 2 is equal to ft divided by m minus km x1 minus cm x2. Okay, then I can write this as x dot 1, x dot 2 is equal to 0, 1, x1, 2, minus k over m minus c over m plus 0 and ft divided by. This is my A matrix I talked about in the previous, which is the A in a continuous domain, and which I talked about, which is a standard form of the state space model, and this is my excitation, which we call it U. And because I assumed the measurement is acceleration, I need to convert my states, which are my x and x dot, to a measurement corresponding to the sensor data. Then I say my y hat, if you see it here, is equal to minus km minus cm x1, x2 plus ft. Then this is my C matrix. This is my C matrix. You see, I was able to write my second order ODE into a state space form and use it in the Kalman filter. But before jumping into the Kalman filter algorithm to follow the steps, I need to mention one point. This A matrix I calculated, it is x dot is a continuous form of the state space model. We need to convert these to discrete form because the Kalman filter algorithm I wrote was in a discrete domain. Then the first option usually people use to discretize a continuous state space model is either skin. And Euler scheme is based on the first order of the Taylor expansion, which it says, I can say, simply speaking, we can say that x dot is equal to xn plus 1 minus xn divided by delta t. Then xn plus 1 is equal to x dot d delta t plus xn. And because this x dot is a xn, then xn plus 1 is equal to a xn delta t plus xn. Then xn plus 1 is equal to a plus a delta t plus I times xn. And this is a of discrete. And this a is a continuous, which we calculated here. Okay. Then once you have your the continuous state space representation of the dynamical equation, you need to convert it to the discrete domain. And the first option is Euler scheme to discretize the matrices. But you need to keep in mind that Euler scheme or Euler time integrator is not a good choice, appropriate choice for a dynamical system, for a vibrating system, because it's not it cannot hold the energy of the damping term, and you're going to need some information, and you will see later. I'm going to show you in the future presentations that why Euler scheme is not a right choice for a dynamical or vibrating system, and it's better to go with other choices like Ranjakuta or Hahn's method. These are the good options, which we will talk about it in the next slides. Okay, if right now we have the state transition for matrices A and C, and you know that the C matrix for continuous and discrete space will be the same. And if you need more information how to to discretize the equations, how to write the equations in a state space form, you can go and read it from the standard control books, and which I mentioned one of them in the description. Now, if we assume we know the F, we know the acceleration and the dynamical system, right now we wrote I define my X as X, I call it my state vector equal to X and X dot, which is my displacement and velocity of vibration, which I'm interested to estimate. And my A matrix in a continuous domain is 0, 1, minus K, M, minus C, M. And my C matrix is equal to, I'm going to write it here, so keep the space. And my C matrix is equal to minus K over M and minus C over M. Using these information and linear Kalman filter algorithm, we are able to estimate the displacement of vibration and velocity of vibration. As you see here, what I did, I compared the Kalman filter estimation, which is shown with the yellow line, with the ground truths. But what I did at one point, I forgot to mention, and worth to mention, is that once I was generating the data as a sensor data, I added some noise to my acceleration, and to see how robust my Kalman filter is. Then, as you see here, I assume that I have a noisy data, but I have a certain model, and I was able to estimate the displacement and velocity of vibration. Now, this is a standard system which we can use in mechanical engineering, in structural engineering, for different kind of systems to estimate the states of the system. Then, for example, now I'm going to expand these to the second story building. I assume that we have a second story building. We install 2 different accelerometers at each floor to measure the vibration, and we put this building on a shaker and simulate the building with the artificial earthquake signal. And I want to see then, and here I'm going to show you how can we use a simple linear Kalman filter for industrial case. For example, you are an engineer and you want to test this building and see if the level of the vibration in the second floor of this building exceeds a specific amount, a specific displacement or not. What you do, you just write the Kalman filter algorithm we had for a two-story building. And because you have the acceleration of the vibration in two different floors, you can estimate the displacement and velocity of vibration for each floor and compare and use the threshold you have to see if the displacement of vibration in the second or first floor exceeds a specific amount, the trigger level, or not. And as you see here, I was able to estimate the displacement of the vibration and velocity of vibration for each floor using the acceleration of the vibration, assuming I know the stiffness and damping for each floor. One point I need to mention here is that for this case study, I assume that one of my sensors are not wrong. For example, I assume I only have the acceleration of the vibration in the second floor. Can I use the acceleration of the second or first floor only to estimate the displacement and velocity of vibration in each floor or not? And the result you see here is exactly for the case that I assumed I don't know the acceleration of the vibration in the first floor, and I only measure the acceleration of the vibration in the second floor. And the case will be the same. You just need to write the A and C matrix for a two-story building, and you will have the C matrix like this. Let me write it down for you. For example, you have a two-story building. Your estates vector will be x1 and x2, which are the displacement of vibration in floor 1 and 2. x.1 and x.2, which are the velocity of vibration in floor 1 and floor 2. In this case, you have measurement only in the second floor. Then measurement will be equal to minus K2, plus M2, minus K2, M2, minus C2, M2, minus C2, M2. Oh, this is your C matrix, as you see here, which will be multiplied by your state vector, which is x1, x2, x.1, and x.2. You see, this is the way you can write your C matrix, and for if you have only measurement in one of the floors. And in this case, you have 4 states to estimate. And for 1 degree of freedom, you had 2 states. You see, if you have 1 degree of freedom, you have 2 states to estimate for this kind of system. If you have 2 degree of freedom system or 2-story buildings, you have 4 states. You see, for right now, you can say that I estimated the displacement of the vibration. And if the displacement of the vibration is, I don't know, bigger than a specific threshold like this one, the building starts, the concrete of the building starts cracking. And this is not, this is the threshold that exceeds the allowable limit for this building. Then you can use this one for your reliability analysis or damage quantification in that damage identification in the building. You see, right now I explained you how can we use Kalman filter for a simple state estimation problem. Now I'm going to ask you one more question here. In this system we were working on here, we assumed that we know the stiffness and damping values. What if we don't know the stiffness and damping values in this system? How can we write down the equations, the A matrix, the C matrix, and use linear Kalman filter? And we need to jump back to one of the main assumptions we made at the beginning. I said, if the system is linear and the data has a Gaussian distribution, Kalman filter gives us the optimal solution, and we can prove it mathematically. But right now, we have K, for example, we don't know the K. We have K, which is unknown. We have X, which we don't know. Then multiplication of 2 unknowns is a nonlinear system identification problem. Then can we use a linear Kalman filter here to solve this problem or not? This is This is something that brings us to the direction that linear Kalman filter cannot be used for nonlinear system identification problems. At least we need to find another solution, and that was the question that people asked to develop other type of the other type of the Kalman filter, like extended Kalman filter, unscented Kalman filter, Kubacher Kalman filter. And these are the things that we talked about. We will talk about in the next presentation. Thanks for your time, and hope see you in the next presentation.